Okay, so on Canvas, I posted this document, Midterm 1 Topics. And so here we go. This is what it looks like. And this is what I'm planning. I might make a few changes, but I gotta, the hard thing is figuring out how long to make the test. You have 50 minutes to write down your answers, so I have to figure out the appropriate amount of stuff to put on. I think this can be done in 50 minutes, but I'll kind of look it over and try to think it through. Okay, so it's going to be Wednesday, right here in class. You're allowed one sheet of notes, letter-sized, writing on the front and back, writing or typing, so up to you. And I will send out a seating chart, and so you have that to look forward to. Okay. I'm currently planning for 5 problems. I might cut it down to 4, but the current plan is these 5 things. Okay. So number 1, some vector-based derivatives. All right, and also I'll give you some kind of function in vector notation, and you will find the gradient of the function with respect to a vector. Okay, so for practice, you can look at the OLS loss function in vector form and see how we took the gradient or the derivative with respect to W. Another example is the problem in homework 1, where you found the gradient of the loss function for weighted least squares. And there's going to be, we'll have other functions that, I'll give you another function here, okay? And the important thing is, if it's a function and you're taking it with respect to some vector W, the resulting gradient will have the same dimensions as W. Right? That's going to be a guiding principle there. Okay, another problem will be gradient descent. And I will provide a function of 2 variables. I'll provide some arbitrary starting location and some arbitrary learning rate gamma, and you will perform gradient descent manually. So you'll calculate the updated location at time t equal 1, and then you'll go to the next location at time t equal to 2. Right? So it'll be kind of this manual thing just to kind of make sure you can do gradient descent. Right? I've got a regularized loss regularization problem. I'll provide a small data set, maybe like 3 or 4 points, and I'll provide the equation for a potential line of fit, and you will find the OLS loss, and then you'll also find the lasso loss and the ridge loss. Now, I think this question came up, and I don't remember what answer I gave in lecture. So when you calculate the lasso loss or the ridge loss, you don't include the intercept term. So you just include the coefficients that get multiplied by x variables, or your predictor variables, okay, whatever they are. But the intercept, which isn't multiplied by a variable multiplied by 1, I guess, that one is not included in the calculation of the lasso or ridge regression penalty term. Okay, so I just want to clarify that. Yeah.
Is this different from our homework too when we do calculate?
I think so. I think maybe in the homework it's a little bit off. So maybe I'll send a note to clarify. I'll put it in the test instructions too, just so it's clear. Okay. And then we've got manual, leave one out, cross-validation. So again, here I'll provide a small data set, maybe 3 or 4 observations, along with maybe 2 competing models or something. And you're going to perform leave one out cross-validation for each model. So you're going to provide, I'll provide the coefficient estimates for each model. Model A, when it's fit to n-1 points. And if there's 4 points, there will be like 4 different sets of coefficient estimates for model A. And then if there's 4 points and there's model B, there's going to be 4 different coefficient estimates for model B. And so for each of these things, you'll find the cross-validation error. And I guess maybe you do a quick comparison between the two. Okay? And then maybe some conceptual questions covering material from lecture. And these might be taken straight from the notes. Maybe they require a little bit of thinking. So conceptual questions are there. Okay, questions? Okay, well, we'll leave it at that. Oh, and today's notes right here. Okay. So we, on Wednesday, we introduced neural networks. And so a quick question, if we have n observations, and this is our neural network, what are the dimensions of your matrix X, your matrix W1, your matrix W2, and the output matrix Y? All right, so do you remember? So X is n by 2. We have 2 columns, 2 variables in X. What about W1? What are the dimensions of W1? 2 rows, 3 columns. We've got 2 in the input layer and 3 in the next layer. So it's going to be 2 by 3. W1 is 2 by 3. W2 is 3 by 1 because we've got where W2 represents the weights in the second weight matrix. So we're going from 3 nodes to 1. So it's going to be 3 by 1. And then lastly, Y will have n observations, 1 output. It's n by 1. Okay, so we have this. So I hope that's okay. Oh, just to note, I've got a bunch of slides today. We're not going to get through them all, okay? I'll push some of this off to Monday. Okay, so if we label all of those arrows, we have 6 weights in the W1 matrix. We got 3 weights in the W2 matrix. And when you multiply X by W, you get Z. And then you apply the activation. After you apply the activation multiplied by W, you get Z in the third layer, and so on and so forth. Okay, so here are our weight matrices. The 6 of them, color coordinated. We have the activation function, and the activation function allows us to have a non-linear relationship between the input, one part and the next part. If we did not have an activation function, or if our activation function was just the identity or something, then the output would just be a product of X and some matrices. It'd be X times W1 times W2, maybe add some bias terms or something like that. But it would just be, we would effectively just be scaling things by doing matrix multiplication and things like that. By having an activation function, we can introduce a little bit of a nonlinear relationship, something where we're not just scaling or multiplying. In our case, we're going to use the sigmoid activation function, but you can have one of many other activation functions. Okay, so here we do X times W, and if we did not apply an activation function, it would just be X times W1 times W2. But this activation function, will transform the outputs of X times W1 to something a little bit different. That output gets multiplied by W2, and then we apply an activation function there as well, and we get Y hat. Our loss function is the sum of squared error. So we're going to take the difference between the actual values and our predictions, Y hat. Our Y hats are determined by this process, which we call forward propagation. And what we want to know is we want to figure out the values in W1 and W2 that will minimize the total loss, okay? And for simplicity, we're going to replace the loss function L, which is 1 over n, the mean squared error here, with a J, which is just 1/2. So we're just multiplying this by a constant, n over 2, okay? To go from L to J. So because we're just multiplying this by a constant, whatever w's we find that minimize j will be the same w's that minimize the loss, the original loss there. Okay? This is just off by a constant. And the reason why we do this is just so that when we work with derivatives, we can eliminate some terms and things get just a touch easier. Okay, so now we're going to get into this step, back propagation. Back propagation, well, here, before I get into what back propagation is, okay? So when we say we want to train the neural network, okay? You want to train your model, you want to train whatever it is. That means we're just looking for the values, the coefficients to put inside our weight matrices W. Okay, right now we have two weight matrices. We have weight matrix W1, weight matrix W2. If you have a deep neural network with 100 layers, you might have 100 weight matrices, and each of those weight matrices might have hundreds of terms. And so you might have thousands, maybe millions, possibly hundreds of millions of coefficients to estimate. And training is all about just figuring out what coefficient values to put in your weight matrix. And we want to pick values so that our neural network will make good predictions. And so the way we train it is we say, well, let's find the w's that will minimize the loss function. And to minimize the loss function, we use gradient descent. It would be nice if we could calculate the gradient, set it equal to 0, and solve. But calculating the gradient is a bit of a process. And then trying to set it equal to 0 and solving is just not practical, even for a small neural network. Okay, it gets quite complex, it gets quite messy. So what we will do is we will calculate the gradient, and then we do gradient descent. Okay, now gradient descent is not guaranteed to find a global minimum. It's not even guaranteed to work at finding a local minimum. But a lot of times it does work, and a lot of times it performs well enough. Okay, but gradient descent, because all you're doing is taking steps downhill, sometimes it gets stuck in kind of flat regions. Okay, so just imagine the way you're going to go downhill is you take a bowling ball, you put it on the top of the hill, you let it go, and you just let it roll downhill, right? But depending on like where on, like imagine you're trying to find the lowest point on the UCLA campus. Okay, you just take a bowling ball and you place it somewhere. Now, if you place it at like the top of the grassy hill by Jan steps, it's going to roll downhill, right? But then if you go, I don't know, just outside this door, it's pretty flat. The ball might not roll very well, right? It maybe gets to the street and rolls just ever so slightly. So that kind of stuff could happen with gradient descent. It can get stuck in a flattish region if you have a bad starting location, and things like that. And so, if you are able to, maybe you give it do a couple runs at different starting locations and see if they perform well, or you just kind of try again, things like that. But anyway, we got to find the gradient. We got to find basically the derivative. Now, in our neural network, we have two weight matrices. We have a weight matrix 1 and a weight matrix 2. And so this will require us to find two gradients. Okay, we're going to have to find the gradient of our loss function, which we now call J, with respect to the first weight matrix, and then the gradient with respect to the second weight matrix. The first weight matrix has dimensions 2 by 3, and the resulting gradient will also have dimensions 2 by 3. It will be the partial derivative of J with respect to each of the 6 terms in the W matrix. And then the second gradient, dj with respect to W2, is going to be a 3 by 1 matrix with the partial derivatives with respect to each component in W2. So dj, with respect to the first element, with respect to the second element, with respect to the third element. And if we had bias terms, a B1 matrix and a B2 matrix, we would have gradients there as well. We would have a gradient of dj with respect to B1 and dj with respect to B2. We will not do this in class. That will be an assignment in your homework to figure out the gradients with respect to B1 and B2. Okay, so this process of finding the gradient is known as back propagation. Now, I will be honest. We're going to kind of do this vector-based calculus method of finding the gradients with respect to W1 and W2. But the truth is even if you go to like Google or something and you do a neural network, no one's going to do this. No one really does this by hand. Okay, you have you have TensorFlow or whatever, Keras, and it kind of it does the back propagation for you, and it kind of sees and it kind of looks layer by layer, and it says how is this layer affected by the previous layer? How is the previous layer affected by its previous layer, and so on and so forth. And that's kind of this idea of back propagation. Here, we're going to do back propagation, and the back propagation is kind of an application of the chain rule, okay? So if you think about the chain rule, and you've got some function applied to g, you take the derivative of g, and then you say, what's the derivative of kind of the next thing. And so anyway, that's what we're going to be doing. We're going to be spending the remainder of our lecture and probably a lot of Monday's lecture going through each of these steps here, okay? And it'll take us a little while. Let me go ahead and give you your first view quiz answer for today. And today's first view quiz answer is the letter C. The letter C as in cat. Okay, so we are going to first start by finding the gradient of the loss function with respect to W2. So so remember, the loss function is the difference between what is the sum of squared errors, right? So the errors are the difference between the actual value y and what we predicted y hat, where y hat is determined by that process. Okay, so we're going to say, what is the derivative of the loss function with respect to W2? Okay, so the loss function is 1/2 times the sum of each observation y minus its prediction y hat. Okay, so I take the actual value minus its prediction, we square that, we sum that up. Okay, the derivative of a sum is the sum of the derivatives. So now I have this. Okay, so the derivative of this, and we want to know how does it change with respect to W2. Okay, so when I do this, the 2 comes down, and I have yn minus y hat, and I apply the chain rule, okay? Now, the only term that is affected by W2, when W2 changes, what values change? Only the y hats change, the predictions, okay? The actual values y are unaffected by W2, so there's no need to try to find the derivative or the partial derivative with respect to yn. That just doesn't exist. Okay, so anyway, I apply the chain rule. There's a negative sign in front of y hat, so I'm going to multiply that by -1, and then we apply, and we say we need to know the derivative of y hat with respect to W2. So how do the predicted values change with respect to W2? Okay, so I have this, and if we look at the process, okay, what was prior to y hat, what values do we have? We had z and 3. So if I go back a few slides. So y hat is the result of a function being applied to z3. Okay, right? So we apply the function with respect to z3. So we're going to say, okay, let's see how y changes with respect to z3, and then let's see how z3 changes with respect to w2. Okay, so I'm going to kind of split this into this. Okay, how does y hat change with respect to z3? Okay, well, if we look at this, remember, if we just look at one observation, we take some value, zn, z3 for observation n, we apply the sigmoid or the logistic function to this. Okay, so the derivative of this with respect to z3n is just going to be f prime of this. Right? So if this is this, and we say what's the derivative of this with this, it's basically f prime. Okay, so what's the derivative of the loss function, the logistic function, not the loss function, the logistic function? The derivative of this, okay, so using quotient rule, we have u over v. And so if I say the logistic function is 1 over 1 plus e to the negative t, and I let u be 1 and v equal 1 plus e to the negative t, then we get this, u prime v minus uv prime over v squared, and we have this, and this is the result, e to the negative t divided by 1 plus e to the negative t quantity squared. So the derivative of the predicted value with respect to kind of the value coming into the activation function z3n is going to be this. Now, for notational, we might just leave it at this, but we'll keep in mind that f prime represents this function. All right, is that okay? So all I'm doing is where we left off, I'm going to replace this term with f prime of z3 for observation n. Okay, and so let's see, how does this z3n change with respect to w2? So during the forward propagation, we said you're going to take the values, the second activation values, the activated values at the hidden layer, they get multiplied by the second weight matrix. And when you do that, you're going to get your matrix Z3. So if we look at just one observation within this matrix Z3, okay, we just look at the nth observation. This is going to be the result of taking the nth row in the A matrix. The A matrix represents kind of the three values in that hidden layer. Okay, so there's three values. So we have one row of three values, and they're being multiplied by the second weight matrix, which is 3 by 1. And so when we multiply these two things together, we get a 1 by 1 value. So we want to know what is the derivative of this with respect to W2. So for this one observation, with respect to W2 is going to be what? W2 is a 3 by 1 matrix. So derivatives with respect to a column vector or column matrix will be a column matrix itself. It's going to be A2 transpose, right? It's going to be this nth row of A2 transpose. So the derivative of this with respect to W2 will be A2 transpose, okay? But just for that one row, just for that one. Is that okay? Okay, so if I plug that in, I'm going to get this. Now, this is a little bit, so we're right here, okay? So here I have this so far, if we look at this, if we just say what is, we've got n observations and we're summing them all up. Okay, each of these things are just 1 by 1 values, right? This is a 1 by 1 value, this is a 1 by 1 value, and Zn3 is a 1 by 1, okay? So this is all a 1 by 1 scalar. This A2 transpose, okay, is a 3 by 1 matrix, right? And And so this result is 3 by 1, and then, so you're imagining each observation produces kind of a 3 by 1 matrix, and we've got n of these things, and so we're basically just adding on all n observations. And so the result will still be a 3 by 1, but each one consists of n values being added together. Now, can we get rid of the summation by, rather than looking at the nth observation in y, can we just take the entire matrix y? Okay, the entire column matrix y has dimensions n by 1. Okay, and the entire column matrix y hat is also dimension n by 1. So I can do that, and this is n by 1. This product here is n by 1. If we take the entire matrix z, there's n observations in z, but if we just take the entire matrix z, then this is also n by 1. Okay, and then if I say not just look at the nth row in the matrix A2, but if I take the entire matrix A2 transpose is going to be 3 by n. Okay, and if we look at this, the dimensions don't line up. Okay, I've got an n by 1 multiplied by an n by 1 multiplied by a 3 by n. Right? We need the result that we want. What are the dimensions of, what should the dimension of j with respect to W2 be? It should be 3 by 1. It should be 3 by 1. Okay? And what we really want, if we think about this, is, I don't know if I can do this over here, but if you think of what dj is with respect to W2, right now it's the summation of each of these things. Basically, we have a 3 by 1, okay? And so basically it's for, this is observation 1 plus observation 2 plus observation n. Okay, we've got 3 values. I shouldn't put zeros there. But basically this is the partial of j with respect to dw2, but for observation 1. Okay, and we've got the same thing here. For all of these things, and we're adding them up. We've got n observations, and so the result is still just going to be a 3 by 1, right? So each of these things, this is going to be a summed up term. This is a sum. This is a sum of all n observations of dj and dw, et cetera, et cetera. Okay, for each of these things being added together. And so we want to see if we can do matrix multiplication so that we don't actually have to deal with the sums themselves. Okay, because a lot of times when you do matrix multiplication, the summation is implicit in the multiplication operation. Okay, so if we think about each element, what is being multiplied when we do these element operations? Okay, each observation here, or each value here, gets multiplied by this value here. So what we're going to do is we're going to do element-wise multiplication, okay, and whatnot. Okay, so if we look at just one observation, this one observation for the nth observation, okay, we can rearrange these terms, right? If we look at the individual values, I can take this, multiply it by this scalar, and I can take this 3 by 1 and move it over here. And that's not going to change anything up, right? I can rearrange these things. And then if I drop the subscripts and I replace this, rather than just the nth observation, so rather than just looking at that one row in the matrix A, Okay, if we look at the entire matrix A, the entire matrix A is going to be 3 by n. We've got n observations. So we're going from that one row, the nth row in A, to the entire matrix A. We've got 3 by n. Okay? And rather than just looking at that one observation, yn, and subtract off its prediction, y hat n, which is just a 1 by 1 scalar value, we're going to look at the entire column. Okay? The entire column is n by 1. These two things now multiply. I've got a 3 by n multiplied by an n by 1. Okay? Now, what about what's happening here? Okay, this is a scalar value being multiplied by a scalar value, and we want each of these things to be element-wise multiplied. We want the nth observation here, the nth value, the nth scalar value, to be multiplied by the nth scalar value here. Right? If we're looking at the first observation, we want that first observation multiplied by the first observation. When we're looking at the second observation, we want it multiplied by the second observation. Okay? So here I'm going to use this symbol. This symbol is going to represent element-wise multiplication. So I've got a column of n by 1 values, and I've got another column of n by 1 values, and I'm going to just multiply them, and I want to preserve the fact that it's still n values. Okay, so that's going to be that's going to be element-wise multiplication. This is not like a cross product. A cross product would take n observations and n observations, or n values and n values, multiply them and add them all up. We don't want that. Okay? We want to preserve that this is still going to be n by 1. So I'm going to do y minus y hat, element multiplied by f prime of z3, which is also n by 1. We multiply those things together. So this result is n by 1. And if I do a2 transpose multiplied by this, okay, the result will be 3 by 1. Okay? And this is also done in the Welch Labs video. And the result will be 3 by 1. So dj with respect to W2 will be a 3 by 1 matrix, which is what we want. Okay, so I've got this 3 by n multiplied by this n by 1, we get a 3 by 1 matrix. Let me go ahead and give you your, did I already give you 1? Okay, so your second view quiz answer is D. D as in dog. D as in dog. Second view quiz answer. Okay. Is that all right? So it's important when you try to do this work, always write your dimensions underneath, because otherwise, if we didn't write any dimensions underneath, you might not recognize that, like, oh, you can't multiply these things together, right? If you when you put the dimensions underneath, you realize, oh, now we're having some dimension mismatches. And when you have things next to each other, you recognize, oh, I actually need to have element-wise multiplication or something, something similar to that. Okay, let's see. Now we are going to try to do the same thing, but we want to find the gradient with respect to the first weight matrix. Okay, so now we want to say, how do the predictions y hat, well, how does the loss function change with respect to W1? And the first part is all kind of very similar, because we're just saying, how does the loss function change? How does it change with respect to W1? And the first part kind of follows the same process so far. All right, but this is where things change a little bit, okay? So we want to say, well, how does Z change with respect to the first weight matrix W1? So we have to say, well, how does A2 change with respect to W1? Okay, so here we're going to ask now. The question is, how does Z change with respect to A2? And it's not with W2. So we look at this and we say, oh, how does Z change with respect to A2? Z is the product of A2 and W2. So Z change, the derivative of Z3 with respect to A2 is going to be W2 transpose. Okay, W2 transpose. So because the nth row in A2 is 1 by 3, so W2 transpose will be 1 by 3. So that's what we have there. So this is going to become W2 transpose. So again, so these are 1 by 1 scalars. This is a 1 by 3. Now we want to know, how does A2, the nth observation in A2, how does that change with respect to W1? Well, we're going to first have to go through the nth observation in Z2. So A2 is the activated values, and prior to being activated, they were the values Z2, okay? And so we just get, we plug Z2, the nth observation Z2, into the sigmoid function or the logistic function, and we get the nth observation in A2. And so the derivative of this is just going to be f prime. Okay, so we're going to just replace this with f prime, knowing that this is a 1 by 3 matrix. Okay, because now this is a tiny bit more complicated because Z2, the nth row in Z2, has 3 elements in it. Okay, because Z2 matrix has n rows, 3 columns, because we have 3 elements in our hidden layer. So the nth observation is one of those rows, three elements in it. So the result here is 1 by 3. Okay. So already our multiplication is already a little bit weird. We got a 1 by 1 scalar. That's fine. But this is 1 by 3 and this is 1 by 3. So how are these things being multiplied together? We recognize, okay, we're probably already going to need to do some kind of matrix multiplication or element-wise multiplication or something, but we'll figure this out in a moment. Okay. Remember, the overall matrix here, J, with respect to W1, is a little bit, this part's a little bit strange, okay? So the resulting matrix, the dimensions of this thing is going to be 2 by 3, right? Because W1 is a 2 by 3 matrix. And we say, well, how are we going to get this? What is the derivative of Z2n with respect to W1? Okay. So if you think about what are the operations happening here? Z2n is a 1 by 3 row matrix. The nth row in X is a 1 by 2 row matrix or row vector, and W1 is a 2 by 3 matrix. So we're multiplying a 1 by 2 by a 2 by 3, and we're getting a 1 by 3. And so we're asking, what is the derivative of this thing, a 1 by 3, with respect to a matrix 2 by 3? Okay, so what is the derivative of a 1 by 3 vector with respect to a 2 by 3 matrix? This is a little bit strange, but if you think about the matrix multiplication between X and W, we can kind of take the partial derivative. And this, I will admit, this is a little bit of a hand wavy. This is not a formal thing. I'm kind of appealing to a little bit of intuition here, to kind of skip over a little bit of maybe the technical math here. Okay, so this is not the official way, but I want to appeal to kind of the intuition here. Okay, so remember, the nth row of Z2 is a 1 by 3. So I've got a 1 by 3 vector, and the way we're getting that is we're doing matrix multiplication between a 1 by 2 and a 2 by 3. So if we think about what elements go into the result is a 1 by 3, right? I've got a 1 by 2 multiplied by a 2 by 3, and when I multiply these things, the first element is this. This times this plus this times this. That's the first element. The second element is this, and the third element is this. And so we can ask, what if I added something, 0.01, to this first element here? Okay. How much does this change? Okay. The only thing that it will change by, if I added 0.01 to this, that change gets multiplied by xn1, this first xn1. Okay? If I add something over to here, the second element, what gets affected? Okay, this element will change. It gets multiplied by xn1. What about the third element? So any value I change in the top row will get affected by xn, right? So if I add some value epsilon to any of the elements in the top row, the element, okay, kind of if we think of like just the summation of this, okay, will change by xn1 times e. Okay, if I do the same thing with anything in the second row, it's going to change by xn2 by e. Okay, and so the partial derivative, or this is kind of a weird idea, the derivative of zn2, this 1 by 3, with respect to w2, ends up being a 2 by 1 matrix. It's just going to be the transpose of x, of the nth row of x. Okay, because if I mess with any of these things, if we're thinking of just like kind of the summation of this, it will change by just xn or xn2, xn1 or xn2, depending on what we have. So the result of this is going to be the nth row of x transpose. Okay, we're going to take the nth row of x, which is this, and we're going to transpose it. We get a 2 by 1 matrix. And so when we plug all of this back in, we get this. All right. Now none of the dimensions are lining up. None of the dimensions are lining up. What we want is we want the derivative of this with respect to W1. We want this to be a 2 by 3 matrix. Okay, because W1 is a 2 by 3 matrix. So how are we supposed to do this? Okay, and so I'm going to say, well, we want a 2 by 3 matrix. I'm going to kind of just rearrange a few terms so that we will end up with a 2 by 3 matrix. Okay, and so I'm going to take this xn transpose and bring it to the front here. Okay, and it feels, are you allowed to do that? Well, again, if you think about what are the elements that are forming this thing, okay, and if you look at each element, this actually is the proper multiplication that needs to be done. Okay, and we want to preserve the fact that when we do the 1 by 3 times the 1 by 3, we're going to still remain a 1 by 3, so there's going to be element-wise multiplication here. Okay, and this is still a summation. Okay, we're going to have the 2 by 1 times this times this. This will end up being a 2 by 3 matrix, and you're going to have n of these things calculated. You get one of these things for each observation n. Okay, so what we want to do now is we want to drop the subscripts and use the full matrices instead. So I've just copied this thing, and so if I, instead of looking at the nth row only, if I take the entire matrix, okay, x will be, x is an n by 2, x transpose will be a 2 by n. If we take the full matrix here, each of these things will be n by 1. This is n by 1. Okay, so I'm going to have to do some element-wise multiplication here. This remains 1 by 3 here. And this thing, when I expand it, okay, taking the full matrix Z rather than just the nth observation, this becomes an n by 3 matrix. Okay. So we can preserve the dimensions by running element-wise multiplication here, okay? And so this result is n by 1 gets multiplied by a 1 by 3. So this whole thing together is going to be an n by 3. So now I have a 2 by n multiplied by an n by 3 multiplied by element-wise by an n by 3. So this 2 by n times this thing will be a 2 by 3. And then if you do, I guess, the element-wise first, you have an n by 3 multiplied by an n by 3. Okay, this thing will remain n by 3. 2 by n times an n by 3 will give us a 2 by 3. Okay, with all of the summations factored in when you do the multiplication between the 2 by n and the n by 3. Okay, so this is kind of what we have. So we'll take this and this. This is n by 3. This is n by 3. So this whole thing is n by 3. 2 by n times n by 3 yields a 2 by 3 matrix. Okay, again, putting all the dimensions underneath everything to kind of keep track of everything. And so I think that's going to be an important thing. when you are dealing with derivatives with respect to vectors and matrices and things of that nature. Okay, we are going to run out of time here, so the next part is just kind of coding all of this up. Okay, so we've taken the time to calculate the derivatives and the gradients with respect to each of these things, and I think on Monday we'll take a look at this, at coding all of this up. Okay, let's go ahead and wrap things up here. Let me give you your last view quiz answer for today, which is the letter A. A as in apple. A as in apple is your last view quiz answer for today. All right, well, have a good weekend. Happy Easter to those of you who celebrate, and we will see you on Monday.